All right, let's answer some questions about things that go around the sigma symbol. We'll use an arithmetic sequence and series to do that, to show that. Let's go ahead and consider the following arithmetic sequence, a common difference of 3. All right, and let's consider how to write the arithmetic explicit formula for it as versus recursive. Our formula is a sub n equals a sub 1 plus, and then the common difference times n minus 1. And that creates the formula for us, the explicit formula. All right, let's go ahead and fill that in. Our first term here is a 2, so a sub 1 when n equals 1. A sub 1 is 2. The common difference here is 3 between each term. That is an added difference in this case, since the terms get bigger, and then times n minus 1. So we've got 2 plus 3n minus 3. And when we put all that together and combine like terms, we get 3n minus 1. So this is our a sub n explicit arithmetic formula. Okay, we'll go ahead and put a little box around that. And then we'll write explicit formula here so that we know what that is. All right. And at this point, we're going to go ahead and determine which term of the sequence 59 is using our explicit formula. So we're going to put into this formula, we're going to put in our 59 as the last term, or the nth term. 59 equals, and 3n minus 1. We're going to add 1 to get 60, and divide by 3 to get 20. So that tells us that 59 is the 20th term of the sequence. So that's a sub 20. All right, let's write these in here. This is a sub 20. This is a sub 1. Okay? Now, let's consider sigma notation for this. We'll come down a little bit and put our sigma notation. And we'll talk about the things that go around it. Now that we are using a specific arithmetic formula, let's make this a series. 2 plus 5 plus 8 plus 11 plus 14 plus ... plus 59. We now have a series, all right? And we're going to use sigma notation to represent that series which came from the sequence. We're going to start with the explicit formula beside it, 3n minus 1. Beneath the sigma notation, we have the lower limit as our index. So we're going to put I or n equals, all depends on the application. We'll put n equals since that matches with what you've been seeing so far. So we're going to start with the subscript of the first term in our sequence or series. So the subscript of that term is the first term meaning n equals 1. And that even though that term is a 2, we don't put a 2 here. We represent this as the index or subscript of the first term of the series. The top number is going to be the upper limit, and this is determined by the last term of the sequence or series, which in this case is the 20th term. It is a 59, but that's the value of the 20th term. What we want to go here is, once again, the subscript of that term in the sequence, and that is the 20th term. So this is a 20. All right, so once again, 1 representing the subscript of the first term in the series or sequence, 20 representing the subscript of the last term or the nth term of that sequence or series. Now that we have this information written, we have successfully created sigma notation for this series using that arithmetic sequence, and now we're going to solve it using our S sub n formula. So S sub n for arithmetic, this is the partial sum formula for an arithmetic sequence or series, in this case a series. n over 2 times a sub 1 plus a sub n. All right, there's our formula. The n represents the subscript of the nth term of the series, which in this case is 20, because we're finding the sum of the first 20 terms of this series, so s sub 20. And then we plug in 20 for n to get 20 over 2, which is 10. Our first term, again, was 2. That's the value of the first term, a sub 1. And then the nth term, in this case, is a sub 20. And we know that a sub 20 is 59. So 59 goes here. And then we put all that together. All right, so we get 10 times 61, which is 610 for the sum of this arithmetic series. All right, so there's our answer if we're looking for the nth partial sum of this arithmetic series.